same at this point, and this stays the same at this point. Okay? Like the nozzle had zero velocity almost upstream, 30 meters per second downstream. It's not the same velocity. Steady flow means although the velocity changes with distance, with time, it will remain 0 and 37 or whatever you found. The second one very important, frictionless flow. Okay? Now, the assumption is that you neglect any frictional effects. Okay? Is this true now in our cases? Like the flow in this pipe. Do you believe that as the water moves along this pipe, there is no friction?
No.
There is friction due to what? Or between what?
Layers of fluid.
Between the layers of fluid in between in general, but more important,
The fluid at the wall of
the fluid and the wall of the pipe. So as the flow is constricted between the two walls of the pipe, well, the pipe is, circular pipe, so there is friction. That needs to be included in the Bernoulli equation. We're going to do it later. Now, there is no shaft work. So if you have a turbine, if you have a pump, so what does a pump do to the system? Adds more energy, okay? Let's say you want to get the water from this location down here up to the top floor. Well, you need a pump, so you need to add energy. By the way, how much energy do you need to go from here all the way to the third floor? Equal to what? MGH, correct. So actually the height, the pressure head, as we said, P over gamma, which is the height from this elevation to the third floor. How many? Do you think is the height of this floor? Of the ceiling to floor?
6 feet.
Is it 10 feet?
No.
10 feet times 3, 30. So if I want to go to the third floor, I need 30 feet
30 feet.
of available pressure head, extra energy. So as long as those don't exist, you can use it. Now if they do exist, and if you have a pump or a turbine, you will have to modify the Bernoulli equation. Incompressible flow, we said that the density needs to remain constant. Here I can tell you that we're not going to deal with anything else, so it's going to be incompressible. Heat transfer, obviously, but we're not going to do any cooling because there's no thermodynamics. And flow along a streamline. Remember, we apply the Bernoulli along a streamline unless there is what we call as irrotational flow, which means we neglect the vorticity. Now, this is a little bit difficult to comprehend, but the streamlines, we assume that the streamlines move what? Like this, in the pipe, right? This considers that there is no interaction between the layers. So that's why they call it a zero-rotational flow. Now, in reality, how do you think the flow looks like in the pipe?
Rough, turbulent.
More like I don't want to make waves now, but the particle moves in a weird directions, which is actually turbulent flow. I'm glad you said that. That's chapter 14 that I want to go through. But if you consider it irrotational, that there is no rotational motions of those vorticities and so on, you can still apply the Bernoulli equation. So, more important for us, for this class is, well, guaranteed is steady, incompressible, and no heat transfer. That's guaranteed. But what will change later is friction, those two, friction and shaft work. So we may have friction and we may have pumps, turbines, and stuff like that. So there are some cases that you may have additional frictional losses in the system. Yes.
The vorticities that you talked about, so we want vorticities to use Bernoulli's equation? Is that what we're saying?
Well, we said that if there are vorticities or high vorticities, you cannot necessarily use the Bernoulli equation.
So if it's laminar, we can then
Yes. But I'll tell you from now, even if it is turbulent, we're going to make the assumption of irrotational, so we're going to use it all the time.
Is there anything that works for turbulent? Is there a formula for turbulent flow?
Yes, but now it's really out of the scope. Turbulent flow is more difficult. I have to go back and look also, and it's not so simple. Because really the turbulent flow is a chaotic flow, there is no, it's turbulent. So we will stick with the idea that later on, even with turbulent flow, we're gonna still be able to use the Bernoulli equation. So out of those elements, I can tell you the sudden expansion is something that you may look. And what's the issue with the sudden expansion?
Drops pressure.
Exactly, we saw that with the case of the nozzle. Long, narrow tube. What's the issue of a long, narrow tube? There are two issues. Eh?
The more the surface area,
If the area is very small, if it is a very narrow tube, that means the wall of the
a lot of
how's
friction.
it gonna overflow?
Well, in general, just an idea.
Oh, overflow, yes, of the tank, yes, but that's a different case. But if it is very low, if it's very small, the pipe, or the tube, the effects of the wall in that pipe are very significant to the motion of the flow.
Pressure's gonna be low because there's not much surface area, and two, it's, the velocity's gonna lower over time because energy's gonna be lost as it hits the wall, hits the walls and.
Correct.
And the curves.
There's more surface area in a long narrow tube
Yeah.
Yeah, in other words,
compared to the volume anyway.
if I now will exaggerate, if I have this pipe, okay, it has some flow, okay, and those are the walls of the pipe, and if I have, with a big exaggeration, the same flow in this little pipe, well, the walls of this pipe play more important role than the walls of this pipe in the overall flow because of the volume, okay? So actually three things. I heard another thing that I didn't even pay attention. So one thing is the size of the pipe. Obviously, the smaller the size of the pipe, the more losses you expect in the system. The lengthier the pipe, more resistance, more losses in your system, and also what?
More curves.
More curves, more losses in the system. Instead of having a pipe that goes straight from 1 to 2 like this, if you do all this extra, you have more losses in the system. So that will affect the Bernoulli equation.
And, but in some cases, you need more curves in a pipe because you actually need a
Intentionally, yeah, of course. Intentionally, you may want to have this weird layout to reduce in the refrigerator.
Yeah, we want to have more layers so that the system takes more.
Correct. What is the third one? The valve. And the last three, we're not going to see them. So, but the first at the top, those three are important. You see, what does the valve do there? It constricts what? The area. So that creates an additional loss in the system. So all those things are losses. Those losses, somehow, we need to include them in the Bernoulli equation. Okay? And I will stop here, okay? And